So thanks everyone for still being here. I'm gonna present in the next hour one of the tasks of the SoccerNet Challenge 2022, in particular the action spotting and the replay grounding. So my name is Silvio Giancola. I'm a research scientist in KAUST. KAUST is a university in Saudi Arabia that is focusing on several aspects, including computer vision and artificial intelligence. And I'm very excited to present to you the action spotting and the replay grounding and the whole SoccerNet Challenge 2022 as it is today. I still remember back in 2018 when I started with the first version of SoccerNet, I would have never imagined it would have grown that much. So I'm only more proud of that. So this live session is really casual. At any time, feel free to interact, ask a question, raise an issue, make a joke. I would like this presentation to be chilled and for you to take the most out of it. And don't be afraid of asking your questions. Don't be afraid of unmuting yourself. Don't be afraid of interacting through the session. The table of content for the next hour for the action spotting and the replay grounding. I will first define those two tasks, how they have been defined, but Anthony already defined them, but I will define them more exactly. We're going to talk then about the different data sets and metrics that are available, the baselines and the state of the art that are also available. So we provide some baseline, but those are not the only methods that are available around. And then I'm gonna talk about like what are the sponsors for those two tasks, what are the price, and how we can get those prices. I'm gonna tease you the current leaderboard for the challenge set. We had a few submissions, so I would like to tease you to show the look, you still have a chance to get some good performances. And then I would like to conclude with some future direction and some insight on how do I believe action spotting can be put in the future. I've been working in action spotting since 2018. I actually defined this task, so I hope I can provide you some nice insight towards what could be next for action spotting and replay grounding. So let's start with the first formal definition of what action spotting is. Action spotting is the task is defining as localizing when a soccer action occurs and identify which action class it belongs to. So when you have a long video of 45 minutes of a first half or second half of a game, you have some specific actions in the game. And those actions are defined by the rules of soccer by a specific moment in time where something happened. Like a goal, for instance, is when the ball crossed the lines. The card is when the referee showed the cards. The substitution is when the player clapped the hands of the player outside and enter. So we believe that those actions, different from what is already existing in the literature, which is temporal activity localization, do not have specific boundaries. There's no like start of the card or end of the card. It's a bit blurry, those limits of when an activity starts and ends. So we decided to define this new task as defining the single timestamp on which a card is shown, the single timestamp when the ball crossed the line, and so on and so forth for 17 classes of actions. So again, the action spotting is defined as spotting, so looking at the time, at the exact frame the action occurs. And those are defined by the rule of soccer. The penalty is when the player, for instance, shoot the ball in the penalty in the penalty point. The goal happens when the ball crossed the lines, and so on and so forth. And in total, what we've defined with action spotting over the last years is that we narrow it down to 17 interesting classes of actions. And we have gathered over the last years 110,000 annotations. Those annotations usually include the time, the specific timestamp that action occurs in the game, the class of that specific action, the team that actually performed that action, and whether that action in the broadcast that is provided with with the SoccerNet, whether it is shown or not. That is actually quite interesting because sometimes when the ball get out of the field, or there are some specific action that are not shown directly in the broadcast, but you can guess that that actions actually occurs. Okay, so that's for action spotting. So again, finding the exact frame an action occur in the game. Then recently, last year actually, we defined with our colleagues of SoccerNet V2 the task of replay grounding, which is somehow an advanced action spotting. In particular, in the task of replay grounding, we're looking at localizing when an action that was shown in a replay. So you have like some actions that are shown usually in the broadcast, it's a replay, so it's not what's happening live. That specific sequence, we want to localize the action spot that corresponds to that specific action. So localizing when an action shown in a replay occurs in the complete broadcast game. So that is quite interesting because it makes us understand, it provides us with several point of view of the specific actions, and it's worth also investigating because if you create your broadcast, you may want to also to predict later on what type of replay should I actually play at specific time, and you can understand some patterns in here, for instance. So the replay grounding is basically, again, a spotting task somehow, is spotting not all the actions that occurs within the game, but just the action that is shown in the replay sequence. Again, it's the same actions, it's just different views, like you can see here in that example on the right and in the center. So on the right, you have a specific replay of an action goal that was performed by that team that I forgot. I think it's Liverpool or Swansea in that case. We want to spot exactly the action when that action occurs. Okay, so it provides like maybe more views. And we gathered over the last years 32,000 replay sequences, and they're all linked with their corresponding actions. Now, when we talk about dataset, I'm reusing like the slides of Anthony here. We have different version of the dataset that has been created over the years. In that specific task, what we are considering is actually the annotation that come from SoccerNet V2 paper, that are basically all the action timestamps that were annotated, 110,000 of them for 17 classes of actions, and the different camera changes timestamps. So we have 13 classes of cameras, and when we have a replay, we also linked that to the main action in the game. So we have several annotations that, and we are focusing mostly in those two tasks with the annotation that comes from SoccerNet V2. So I invite you to read the paper to understand more the details of what those data are. But here are a few summary of what SoccerNet V2 is. It's a total of 300,000 temporal annotation. We have 17 different actions, such as, for instance, ball out of the play, throw in, foul, indirect free kick, clearance, shot on target, shot off target, and so on and so forth. And we also have annotated the different cameras and whether or not this camera actually show a replay. So in broadcast, you actually have a limited set of camera that are shown, that most of them are maybe like the main camera center from which we are all familiar with, but we also have the main camera left, main camera right, the main behind the goal. There is the new spider camera that exists since a few years now. You have camera showing the public, and you have the others one. So those are the type of annotation provided by SoccerNet V2. And whenever that camera shown is actually showing a replay, that replay is linked with an action. Okay. So in terms of amount of data that we have gathered here in that specific case for action spotting, this is the leaderboard that comes from the paper SoccerNet V2. Don't mind the results. What I want to show you is the different classes, the distribution of classes, action classes that are represented in that specific case in the test set. As you can see, all those 17 classes, they are kind of distributed not equally. We have way more ball out of the field than you actually have red card happening or penalties, for instance. So the distribution is really, really unbalanced, which makes action spotting quite challenging. because actually you are more interested in spotting a red card, for instance, than you are spotting a ball that goes out of the field. Why is that? Because the red card is something that you might want to inform. This kind of information that is really really interesting about that game. Oh, there was a red card. If it's Messi getting a red card, you want actually to know when that happens, because you can reuse that content later on to do highlight or gather statistics, for instance. So very unbalanced data sets, that makes it challenging. So in total, like Anthony said before, we have 550 games, which represent more than 825 hours of videos. All the videos come from the seasons ranging from 2014 to 2017, and they come from the Big Five competition in Europe, so La Liga, Ligue 1, Serie A, Premier Leagues, Bundesliga, and the Champions League, which is the European championship that is very interesting. And I hope you have watched the game yesterday of Real Madrid against Manchester City. It was a really great game. So basically, we kept 50 exclusive games, 50 games out of 550 that are used exclusively for the challenge. We kept them segregated. We are not sharing the ground truth with anyone else. And it's basically the set of videos of games that we are using to evaluate the performances of all the participants. Okay. So in terms of data that we are providing, as I told you, there is like a lot of games. What are we exactly providing? Since last year, we were providing two types of videos, the untrimmed high quality videos and the low quality videos. The high quality videos is a untrimmed version of the games that comes to many different resolution, many different frame per second, frame rate, that we unified into the low quality videos that is 224 by 398 at 25 frames per second. Now, why did we choose 224, you might ask? We choose 224 because, I don't know if you know, but most of the video encoders in the literature do not use the full resolution of the image. It actually first downsample the resolution of each frame or the videos into a lower resolution. So actually, we don't need the whole full HD videos to extract meaningful features. So that's why we decided to lower down, and at least the whole data set of the low quality images only fits within 100 gigabytes maybe, while the whole high quality videos fits within like 2 terabytes, which is quite a lot. On top of that, we took the low quality videos and we extract then some features that we are providing to the community. Originally, ResNet features were the most popular one, but we recently know that since from last year, Baidu provides its own set of features that comes from the video as well, and that are more performant so far. So one novelty that we did for this year is that we reunified those datasets. So those videos, especially the format of the high quality videos that was untrimmed before, we actually create the similar 224p videos into a 720p videos that have a constant frame per second and a constant aspect ratio and the resolution. Why is that important? Because we realized that having such a diversity on, first of all, people were starting using high quality videos to extract some player features or field features, for instance, that cannot be done at such a lower resolution as the 224p. So we decided to provide the 720p videos as a unified format that is cross-platform as well, and is that is in suitable format. Okay, that's the novelty of that. Now you might ask, how can I download those data? So we provide a pip package, the SoccerNet pip package that you can install. So pip is for Python packages. I hope you are familiar with Python because most of the code that we're providing is with Python. And we can install that package by just installing pip install SoccerNet. All this code is actually available in our GitHub repository that you can find on the SoccerNet GitHub repository, SN spotting. SN stands for SoccerNet, of course. And similarly, we have another repository for the grounding, SN grounding. Now, just to give you an idea of how easy it is to download the data, it's just a few lines of code. So you just need to do like pip install SoccerNet, and actually can show you that in live. So here I have cloned my repository of SN spotting, okay, and I have the README in front of me here, where I can basically install my SoccerNet pip package, and that has already been installed in that specific Conda environment. So I don't know if you're familiar with Conda. I recommend you to watch some video online about that. I've created a Conda environment where I installed Python. I think the latest version available in Conda, which is 3.10, for instance. I've installed pip. I've installed SoccerNet through pip, and it was already installed, so it doesn't need to install that anymore. And now, how can I download my data? It's extremely simple, and we put a lot of efforts in that, and it can be done with Python. So if I have a Python instance, in fact, this is Python 3.10, as I mentioned to you, we can just like import that specific library that is a SoccerNet downloader. So it's a utility to download. I create a SoccerNet downloader entity with local directories that shows at a specific path where I want to store that information. And then I can just download specific files for specific splits that we are recommending, the trained validation testing set that are used in SoccerNet since the beginning, or maybe the challenge set. Here in particular, I will be downloading the labels from SoccerNet v2. And as you can see, it will gonna download them into pass to SoccerNet, and it's gonna download a list of labels in particular, some of them already existing, and you're gonna see appearing here on the right. Okay, so this is like how to download the labels, for instance, for the spotting task. If you want the labels for the grounding task, it's called labels-camera. It's explained in the GitHub repository. But then what if I want to download the videos, you might ask? So I'm stopping the download, so it won't fill my memory. If I want to download the videos, I can also download the videos, the 224p and the 720p. For different splits, including the challenge, for instance. Now, the only particularity is because those contents actually contain some copyright, we ask you to fill an NDA, a non-disclosure agreement. That is just a way for us to protect us, that we are sharing some data, there are some copyright, you should not share that with everyone else. People should sign a non-disclosure agreement so those data stay between each other. So once you file that NDA, that you will be provided with a password, and you will be able to download the videos. Now, do you need to download the videos? I would say no, because if you want to run tracking, if you want to run the baseline in spotting, in action spotting, all you need actually are some pre-extracted features, and we have already extracted all the features for the whole challenge. In particular, we have the ResNet features, and we have the embeddings that were provided from Baidu. And if you want, you can download them directly by downloading the list of games, all the games, all the encoders, all the features for all the games for the different splits. And again, it will download them one after the other at a decent speeds. I have to say that those data are stored locally here in my university, so I can have speed up to 100 megabytes per second. Okay, so that is a way of how to download the data. What is the structure of this data? Here I have downloaded all my data in a path that is called path to SoccerNet, and it's basically here. Basically, the SoccerNet is for the spotting task and for the grounding task. They are organized within in between per game, and each game is organized by championship, by season, which year of the season, then per game. And then for each game, you have the first half and the second half that are split between the different MKV, for instance, which are the video at 224p and 720p, or the features that are in an NumPy format for the Baidu Soccer embedding, for instance, or the ResNet in this specific case. Okay. So basically, we provide code for you to download very easily all the data. And you can do that for SoccerNet spotting and for SoccerNet grounding. The only difference is that the labels come from a different source, which is labels-cameras. All right, I'm going to talk now about the different metrics that have been used so far and the different metrics that we have introduced for this new challenge. In particular, for the action spotting, we have a bunch of labels that, as I mentioned, that are basically timestamp for specific actions. So the labels, if you open labels-v2.json, will look like a big text file like this that tells you like what is the game we're talking about, and a list of annotations in that query, in that key, that tells you, that give you a dictionary about like, oh, there is an event called, let's say in this one here, the throw-in at the first half, minute 1 and 26 seconds. This is the time in milliseconds, the exact time in milliseconds. The labels of that action is called throw-in, and the team that belongs to that is actually, sorry, the team is away, and the visibility is whether that action was shown in the broadcast or not. And in this particular case, that action was not shown in the broadcast, which was the case for the kickoff, for instance, that happened obviously at the minute 0-0 and at the time 0 of the game. From the team home, means that the home team started the kickoff of that game, and usually this event is actually visible. This is like the files of the file of the labels, and the file of the predictions looks very similar, but rather than having a key called annotation, you have a key called prediction, which is again a list of all the actions that I believe I have spotted. Like for instance, in this specific case, at the first half, minute 0, 49 seconds, I have detected, I've localized a throw-in. The exact position in milliseconds are actually 49,000. So there's no milliseconds. It can give you like some more precise, more precision in that. It happened in the first half, and I give them a confidence score. I will tell you later why the confidence score is actually important. We are expecting that everyone is going to use like some deep learning, and usually those predictions come with a confidence. If you don't have a confidence in your method, just put 1 and that will work. Now, taking those labels and those predictions, how do we get the metric, and how do we get the famous average, mean, average precision? In short, it's average, mean, AP. Okay, how do we get them? Actually, we didn't like invented that on our own. That we got actually inspiration from what is done in video understanding. Some of you might be familiar with video understanding, and in particular with the task of temporal activity localization. In particular, in temporal activity localization, we define activities with a beginning and an end. So if we have an activity that spans within 5 seconds and we predict something on top of that, we're going to check for the temporal intersection over union. And that temporal intersection over union, if it is within a specific threshold, we're going to consider our prediction as a positive, either as a true positive or a false positive. So we did the similar things with the action spotting. The action spotting, we actually returns a mean AP that is given towards like a delta tolerance. Here in that example, we have 2 ground truths that are defined with those triangles, and we have 2 predictions. If I'm defining a very short delta of only 5 seconds, I will actually have that span. So basically, does any of my predictions are close to those 2 ground truths? And I would say, no, none of them actually intersect, are actually as close as 5 seconds to the ground truths. So I have 2 false negatives because I have not spotted any ground truths, any prediction around my ground truths, and I have 2 false positive. I have 2 positive in here that are actually not exactly my ground truths. So increasing that delta will increase the amount of true positive and reduce the number of false positive and false negative, which will lead to better recall precision, that will leads to better average, better mean AP and better average mean AP with different value of that delta. So let's dig into more details about what I just briefly mentioned. So for each class separately. So first of all, I told you we have 17 different classes. We're going to take each class separately. We check the predictions are within a certain fixed interval, a time interval delta around the ground truth, and define the true positive, false positive, and false negative. So basically, are we within this temporal threshold? Then for each delta, again, for each class as well, we are going to threshold all the prediction based on the confidence score. And we're going to count all the true positive, false positive, and false negative, and we're going to compute the precision and recall. So precision and recall are well known in artificial intelligence. I do believe that you know what those two are, and we're going to actually create the precision and recall for a given delta and for a given class for all the predictions of all the videos. That defines my precision and recall curve like this. Again, basically recall tell me like, so precision is like how precise are the predictions I'm doing. And recall is how many of them did I actually miss. And of course, if you change that confidence, you're gonna have a lot of false positive that will give you a better precision, but a worse recall. Anyway, after we have defined the different recall precision, we approximate that precision recall curve with something called like the rightmost max value. It's a standard procedure for average mean AP. And we're going to compute the area under the curve by an 11-point approximation from 0 to 1. Then we're going to take the area under the curve that gives us the average precision. And this will give you a specific average precision for one particular delta. So we're going to average, we're going to repeat the average precision for all the different sigma, in that specific case from 5 seconds to 60 seconds. And we're going to compute the area under the curve of that specific average precision in delta. And that is called the average AP. Now we're going to repeat that for each class. And that will give us the mean in the average mean AP, all right? So that's basically how it is defined. You can understand it as temporal activity localization that have mean AP at a specific temporal intersection over union that give you like some information whether you can consider like a specific prediction as a positive or not. We are defining like how close it is to the ground truth. Now, last year, what we did is that we defined the average mean AP with those delta tolerance that range from 5 to 60 seconds. Now, those are very loose average mean AP. Why is that loose? Because a prediction, I can predict a goal that happened like maybe 60 seconds after the real goal really happened, and I'm still considering that as a positive, a true positive, which is a bit misleading. Maybe I'm actually not spotting the goal, but maybe the replay that happens right after that. So we wanted to be more precise within this average mean AP by reducing the delta tolerance in this metric. And for that, we introduced what we call the tight average mean AP with delta ranging from 0 to 5 seconds. So basically, we are more looking into like very close predictions with respect to the ground truth rather than something that is very permissible. Now, of course, if you take the current state of the art or the current metrics, those performances will drop a lot. So here you have all the participants from last year challenge. And as you can see, they had like some very high performances that originally ranges from 40 to 50% up to 75%. So we said, okay, maybe this metric is a bit too permissible. What happened if we're gonna provide now the leaderboard in the tight average mean AP? And interestingly enough, the two methods that were state of the art before last year, which is Baidu and also using NetVLAD plus with Baidu features. And I forgot also, I think the Oppo metric also, the Oppo submission was also providing similar ranges. They're actually still like, they will lose like 1/3 of the performances, more or less. Now, the interesting thing is that those methods were actually fine-tuning the features. And they won't lose that much performance, like maybe 33% of lose, or at least like 50%. The interesting thing is that this method, AI Image Lab RMS, is actually an end-to-end method that will also fine-tune the features while training, and they only lose like half of the performances, while all the other baseline that we proposed for the previous methods, the performance drops drastically, which means that it's actually extremely challenging to get a good tight average mean AP done to spot very accurately when a specific action occurs. Now again, how can you simply perform get the performances of your results, right? So we provide some baselines, and in those baselines we extract some all the results in a JSON format like I showed you before in the prediction. So you can copy the same structure for that. And then we zip them inside a zip, and we provide actually code for you to evaluate that locally on your workstation, at least for the test set where you have the ground truth. So we actually have in the GitHub repository a folder called evaluation, where we provide those evaluation spotting code, for instance. I'm going to show you how it works live. So actually, I already run that, and it's in here. Basically, the way you can do that, we have created in the SoccerNet Python library a function called evaluate for each specific task. And you can use those functions to evaluate your specific predictions of one specific file with respect to the ground truth, with some specific parameters. And here in particular, what I did is that I run my evaluation given like where is my SoccerNet ground truth, given that my predictions are actually some methods, and this is NetVLAD++ that came from last year, and with which metric in particular. This one is the tight, not the loose metric. And what it does is simply it's going to read all your predictions, and it's going to evaluate whether the performances of in average mean AP of those specific evaluation, of those specific predictions. So here in particular, I'm looking at the benchmark temporal overall pooling. I've trained a new model called NetVLAD++, and I have a zip file that provides me with the results of spotting for the challenge set and for the test set. So for both of them, then this script in particular provides you with a lot of numbers. It gives you most importantly the tight average mean AP, the tight average mean AP per classes, the tight average mean AP for the visible subset, and so on and so forth. And here in particular, we can see that, oh, look, my NetVLAD++ actually have a tight average mean AP of only 11.16%. And spoiler alert, this is exactly what we have in here, a little bit different because I've retrained that model from scratch. So the performance was not exactly 11.51, it was 11.16. And of course, you can evaluate the same thing with not the metric tight, but the metric loose. Metric loose, is it? And you're going to get the same performances that we mentioned in the loose here, basically. Sorry, for the test set. So this one, 53. Okay. So code is available for evaluation, which is amazing. So you can just like look at those GitHub repo to check that. Same thing with replay grounding. The formats, I invite you to check the format of the replay grounding is a bit different, but everything is explained in our SN grounding repository. Here the annotations are first annotated like what type of camera is it showing from which time to which time. And then when it is a replay in here, we have a link of what's the action it actually is, like that. What's the action you need to spot? What's the action it actually corresponds to? And similarly, the predictions are slightly different because for the list of replays, for a replay that starts and ends at a specific time, you will have a list of detections, and basically you need to spot the one. And of course, you can spot more of them, and then it's a retrieval task, and you're just going to retrieve which one is the most probable. Again, for the replay grounding, we do have code available for, again, just evaluate grounding. You provide them the ground truth of where the SoccerNet path is and where your prediction is. All right, so next steps are actually presentation of the baselines that we provide. So we provide several baselines that we have developed over the last years, in particular for action spotting and replay grounding. And I'm going to present three methods in particular, and the adaptation for replay grounding, which is basically learning how to pool, which was one of the papers from the original SoccerNet and the recent one from last year. Context-aware loss function, which was a CVPR paper in 2020. And then a recent paper, camera calibration and player localization, which was a CVPR 2021 a paper from CV Sports 2021, which basically use more than general features like ResNet frame features, but look at camera calibration kind of information and the localization of the players. But let's start with that first baseline called learning how to pool. Learning how to pool is a very standard method, I would say. I gave a lot of talks about all the technical details in there, but I want to give you like an overview of what this method does. This method, basically, you have a whole game and you extract features for all of those frames. Okay, so that's why you, for instance, you already have pre-extracted features from ResNet, or you can have C3D, I3D, you can have any type of encoders that you imagine. The embeddings are provided from Baidu, for instance. And then basically you take like a Windows and you're going to pool the information from that specific Windows. And on top of that information, you are building a classifier, a multi-label classifier, whether or not there is an action from a specific class. Now, we're going to train your multi-label classifiers in that fashion, then your frame features or accordingly if you do an end-to-end learning. And the pooling layers can actually be a bit more smart, and you can also like have some parameters inside that you can learn some smart pooling in here. This is for the training phase. And then once you have trained your pooling layer and your classifiers, you can simply have a sliding windows that will provide you with the actionness in time for a specific action. So for a specific action class. So here, for instance, you have the activation of specific actions around specific ground truths, where we can see that, I don't know, for that specific example, we have a high actionness that would correspond to an action occurring at that specific time. And you can take the segment and then have some smart way of inferring, regressing where is that exact timestamp of that event. Now, the results for all the events are like, it looks like this. This is like an example from SoccerNet V1 where you only have card substitution and goals. And the idea is that it will provide an actionness that you can extract the spotting out of this. Now, learning how to pool, there is a lot of flavors that has been developed over the last years. First of all, you can have multiple different backbones. You can have ResNet 152 backbones. You can have the Baidu encoding that were the winner from last year. You can have PCA reductions of any of those feature embeddings. You can also have multiple pooling layers, whether it is a simple max pooling. You can maybe want to pool all the features and just learn out of the maximum value of all the dimension. Or you can have some more advanced pooling like NetVLAD or temporally aware type of pooling, where you want maybe to disentangle the past and the future context in those pooling. And then you can have different spotting heads. You can estimate the center of the segments or the maximum value of that specific segment, or couple that with non-maximum suppressions to filter out those values. Now, how to get started with this learning how to pool baselines? Everything is on the dev kit. On that specific link that I'm just providing on the bottom. And is basically, again, in the repository of SN Spotting. Now, just to scroll through this information real quick, basically, this is the README of the temporal aware pooling for action spotting. This is the code, and it's as easy as you create your environment. You need to install, in that case, I was using Python 3.8. You can create your Conda environment, you install PyTorch and everything, Tensor Vision, CUDA toolkit corresponding to your GPU, and you can install some pip packages, including the SoccerNet, for instance. And then training is as easy as running one line of code. Here inside, I invite you to check the source code. It has a main function that kind of like orchestrate the whole thing. The data loader, the model, everything is quite clear and well disentangled in that specific code. And training, I did a training actually just before we came. Once you train, you're gonna have such a user interface with all the users. Like here, I run basically the training of a model NetVLAD++ on a ResNet PCA reduced at 512, and you have a lot of different parameters you can play with, and then it's going to train until convergence, and once it has trained, it's going to output all the results of that specific training with a zip file for the challenge set and for the test set. Those zip files are the one you can submit directly on Eval AI and to get the performances in the leaderboard. Okay. So I'm going to present another baseline, which is a context-aware loss function. That was a CVPR 2020 paper, not CV Sports, was the main conference, so it was quite a good performance. And here in that specific pipeline, what we try to do is, of course, we still have like the frame features that came out of each specific frames, but can we embed like some temporal CNNs, and we have like specific features, and I want to segment different part of specific clips. I'm going to explain you that in the next frame. So basically the whole idea that came into this loss function that we've developed is that when we need to spot a specific action, the context around that actions provide different information. First of all, when we are far before the action or far after the actions, that is basically in the extremum of there, we don't want to detect any action there. Then when we design a loss function, basically design a loss function that take into account the different context around the actions. So if we draw a loss function with the actionness the loss that is actually here, we are going to see that we do not want to have action detected from far away, from far after and far before. Then when an action, when something happened right before an action, like a goal, for instance, it's actually not necessarily contains a lot of information to detect that actually happened. And it's only just after that specific action happened that you have all the information that, oh, a goal happens. So to give you an example of the goal, you don't know it's a goal before the goal actually happens. So we develop a loss function that take that into consideration, and that allow us to reach some very good performances in terms of performances. So here you can see what our loss function would look like in complete. I invite you to read the details in the paper to understand what's happening in here exactly. And on the right, you have the overlap of that loss function when more than one action actually occurs. Now, the way we use that loss function is slightly different from how we use it in the pooling layer. In particular, we created 2 minutes snippet. So we cut the 45 minutes videos into clips of 2 minutes. And in those 2 minutes, we are actually predicting the exact time, the location in time in those 2 minutes when specific actions actually occurs, whether they actually here with where it is exactly and what is the class. And that specific encoding allowed us to do a nice trick, like for instance the iterative one-to-one matching to perform the predictions to the ground truth encoding that provide a very nice performances, like a regression model somehow that would regress how far is an action in that specific clip. Now, once again, this is a very broad overview of CALF, context-aware loss function. I do invite you to read the paper that introduced that baseline. There is like for sure better video online on YouTube already in the ACAD channel that will explain the interesting details of a context-aware loss function. Again, that method is available online. So here, for instance, I can show you what this calf look like. Again, it's as easy as installing, creating an environment. So again, Python 3.8, PyTorch 1.6. So this method is using PyTorch and Torch Vision. And again, it's just like one line of code that allows you for training, but also evaluating the performances. Okay, and again, we actually provide access for the whole source code. You have a main function that orchestrates the whole training that is done by the train.py. We have the dataset that is with the data loader that is on dataset.py, and we have the model that has been defined here on model.py. And everything is PyTorch friendly, so you can have a look. It's really user friendly, and there are again better and longer tutorials on how this KAUST method actually looked like. So then later on, what we did in a paper from last year in Civil Sports, we said, and it was a collaboration with Florian Magera that is also, that's actually gonna present in the next hour our paper on camera calibration and field localization. We said, can we use the information at spatial dimension to help, for instance, a method like context-aware local, context-aware loss function. So can we use the field localization information of the localization of the players in order to learn a better encoding, a better embedding that is not just take the full frame into account, but also into context, like the different players that are playing within the field. And for that, if you merge field localization with player localization, you can draw these top view images of what's the current game is actually, what's the state of the current game, and how can we leverage those features within a method. And again, we provide code for that. And basically, this is nothing else than context-aware loss functions, also called KAUST, with some extra features. The original KAUST methods will just take resident features, for instance, but can we use calibrated data representation with some extra trainable backbone that rely on specific image encoding or specific graph convolution network in order to provide more spatial information about the state of the game? And in particular, what we did is that what the original SoccerNet provide is basically a bunch of features at the frame, like something very global, something that is very coarse, that does not have that much information about where the players are, where the field is, and so on and so forth. So we extracted some information such as the camera calibration, basically the field localization, and the player detections. And we combine this information to create like extra features, such as features that come from those images that we created from those top view image, or the color composition image that that shows, for instance, different encoding, I would say, of this different information. Or we said, can we use like a graph convolution network, for instance, to create some more information about the local position of all those players, to see how they can contribute within the performances of action spotting. Again, this paper was published. We have code for that that is available in two links. We have the version for taking into consideration the graph convolution network, and the one without the graph convolution network that you can use at your wish. It has the same structure with the source code that is extremely well detailed, and again, how to create an environment, how to install the different libraries, and how to start training a model, and how to start evaluating a model. So that's the current leaderboard for 2021 as it is, and we have extremely good performances that came from Baidu Research and Oppo, especially with their new features that were fine-tuned. But of course, the literature review is actually extremely wide, extremely large. And here I listed like a non-exhaustive list. This is a non-exhaustive list of papers that's been published over the last 2 to 4 years old. All the ones that are underlined are the ones that are implemented in our development kit. Now, without going into too much details, we also have codes for replay grounding. Replay grounding, again, so I have a replay of a goal that I want to detect and link that, I would link that to a specific action. And the way we are providing the baselines is simply using a Siamese approach, where we have a replay chunk and we have a video chunk. Again, in the KAUST context-aware loss function, we are sharing the different weight, and we are concatenating those features in order to predict in the video chunk when the action showed in the replay is actually displayed on that specific time. We have code available. I invite you to go to those different links that allow you to start with that. And similarly, we also have a method that is based on the NetVLAD paper. And for the replay grounding, those are the leaderboards that come from last year in particular. As we can see again, the tight average mean AP has a huge drop in terms of performances. And those are this because replay grounding is very recent. It has a lower amount of paper that has been published so far. But I invite you to read those papers to understand what are the state of the art for replay grounding. All right. So without further ado, I only have a few slides left, and I wanted to start by detailing a bit further what are the prize and the sponsor for the specific task. The sponsor is actually Synergy Sports, which is a division of Sports Radar, and they're providing two prizes, $500 each, one for the task of action spotting and the other one for replay grounding. Again, those prize will be given to the best performing methods in the challenge leaderboard. You'll have to, what are your deliverables for you to compete? You need to provide your results on Eval AI, the zip files. You just submit them and you will appear in the leaderboard by May 30th. Again, it's on the challenge leaderboards, not on the test one. And you'll need to send a technical report by June 6th. We highly encourage you to release your code, but it's not mandatory. So if you have some constraints from a company that does not allow you to share code, you are still able to participate. And we also invite you to submit your results, your paper results, your technical report or an advanced version of your technical report to the Sports conference, which deadline is on July 4th. Now, a few words about Sports Radar. So it's a group of Synergy Sports. They are deeply interested in video sports understanding. In any aspect of video sports understanding, Vladimir Sommer, which is also I think here in this Zoom meeting, is also interested in re-identification, for instance, action spotting. But those are only two examples of what Sports Radar are actually interested in terms of video sports understanding. And if you're looking for any opportunity, know that they are currently hiring any talent in computer vision and deep learning. And for that purpose, feel free to send an emails to Vladimir Sommers or just contact him directly because it should be on the chat. Now, without further ado, I want to tease a little bit the results of the leaderboard for spotting for the challenge task. And in particular, we had 2 submissions so far. I've blurred the name just for you not to be biased by who they are, to keep their privacy. But I just want to let you know that there is a participant that managed to get an average mean IP with a tight score, that the previous baseline was 49.56. That's actually the winner from last year, managed to get 60% of average mean IP, which is an impressive boost. And if I should analyze that result with the previous metric, it does that without losing significant performances in lose average mean IP. So congrats to that person. Your identity is still secret, but there are still some room for improvements. I'm very convinced of that. And there is a runner-up on the bottom here that I also blurred his name, that managed to get 40 average mean IP for tight so far. Now, the leaderboard for replay grounding, because it's a new task, there's less maybe IDs, are currently no participation so far. Notice that there is $500 to make just by providing one submission that beats that score. And I'm pretty sure that if you do some hyperparameter tuning, you can beat that score. So you don't even need to create a new methods, but just doing hyperparameter tuning allow you to get better than 19.12. Right? Yeah. So what are the take-home messages that I want to deliver by the end of these sequences? So there is a lot of insight and research direction and hot topic that I believe has not been yet explored in action spotting and replay grounding. In particular, we noticed from last year that fine-tuning the features actually helps. So if we have a better way of training features on the soccer data, this is actually a very good way to boost the performances. And there is a lot of self-supervised, unsupervised, fully supervised method that focus just on improving the capability of those features. Now, a second hot topic I would say is transformers and self-attention mechanisms. Within the recent literature, there is the Baidu submission last year were using kind of a self-attention mechanisms to get best performances. And there was a paper that was recently published in 2021 in the list of papers that I mentioned that is also investigating self-attention. Now, another direction that I think is actually interesting, not necessarily in a transformer-like kind of approach, is that actually all the pooling methods are actually using what a 1D CNN. So the question is like, can we actually just investigate the whole video as a 1D CNN? If you take the features, let's say the Baidu features, and you construct like a 1D CNN in time, usually this does not require a lot of memory, you can investigate like temporal dilations or specific attention mechanism within the CNN, such that you can gather all the information of the whole videos. So far, all of those methods are not able to gather attention or receptive field from far away in time. So maybe investigated and framing that problem as a 1D CNN with some temporal dilation eventually to skip some frames will allow you to gather some temporal context that was not seen before. Another line of direction could be eventually those pooling baselines. How can we couple them with field and player localizations that were used in the context-aware loss function, for instance? Can we do any refinement, whether on the hyperparameter or even in the module itself to allow for tight average mean AP? If I know that I can get like 75% in loose average mean AP, maybe I just need to iteratively refine those spottings to converge towards the tighter spotting. And again, there are some methods in 2021 that investigated end-to-end training, in particular the RMS from Matteo Tomei, RMSNet, that was quite impressive, that arrived third last year, that got some very good performances by training everything end-to-end, basically both the features and the spotting head. And with this, I'm done with my presentation. Feel free also to scan those QR codes to get access to the different GitHub repo. Thank you.